All right, hey everybody. Welcome to the end of the day. Thank you for being here. I know we're all very hot and very tired. Um, I'm Anthony. We're going to be talking about metaprogramming with Kotlin Symbol Processing. I'm just going to call that KSP from now on because it's a little easier to say. So, we're going to be talking about um, four different topics. We're going to talk about a little bit about what is metaprogramming because it's a big word. We are going to talk about a brief history of metaprogramming. We're going to talk about Kotlin symbol processing and how to do that. That's going to be the most of the talk. And then we're going to talk a little bit about AI and metaprogramming and how that relates. So, metaprogramming, as defined in the Wikipedia article, is a programming technique in which computer programs have the ability to treat other programs as their data. That's a little abstract, and what that really just means is that a program can ingest another program and it can create a different program or code that can modify itself, self-modifying code. We're going to talk about two different types of metaprogramming today. One of them is something that you might not really think of as metaprogramming, but that is reflection, called reflective programming. And so most of us regularly interact with reflection. We use reflective APIs pretty regularly, but we don't really think of it as reflection. But it is reflection because it allows code to modify itself. It allows a class, for example, to change the way that properties can be accessed when previously they wouldn't be able to be accessed, and they are able to do that at runtime. More traditionally, what we think of as metaprogramming is compile time program execution. And so that ranges pretty much all the way throughout history. The history of coding is generating code, and that is probably why you're here today, because we're talking about KSP, and KSP is code generation. So that's pretty abstract. We're going to explain a little bit about. We're going to start with a scenario and we're going to build a KSP using that. But before that, we're going to go into some of the history. And we're going to go way back, all the way to 1960 in April, when the Lisp language was published. And you might be a little scared because this is an Android conference and you probably only use Kotlin or Java or the Flutter, whatever, the Dart down there. But Lisp was the first language that had metaprogramming in it. It was the first language that had a representation of itself within the language, and it was the first language that was able to change the way it behaved at runtime. And the reason that this was the first language is that they wanted to build AI, and the only way that you could build AI is with a language that can change itself. And so they developed, the original author of Lisp developed Lisp for this reason, and then all of the derivative languages from Lisp had metaprogramming. And so this is where metaprogramming started 65 years ago. January of 1996, we're going to fast forward to some less ancient history. Java 1.0 was published. And this is important because Java 1.0 had metaprogramming capabilities in the form of reflection. It did not have code generation. And actually, Java 1.0 only had the ability for a program to read its current state. It was able to read class names. It was able to read information about properties. And it was actually not able to change itself. But Java 1.1 quickly came after and introduced the ability to do that. Now we're going to go more forward, 9 years, to JSR 269. JSR just means Java Specification Request. And the JSR 269 introduced the annotation processing idea to Java. If you've been working on Android for a while, you probably remember you might have run into annotation processors. Basically, that's just Java's way of doing code generation. This was called Annotation Processing AP. It generated Java code, and it was released in Java 6. I don't even remember what version of Java we're on right now. So we fast forward to some recent history. March 2017, we have the KAPT capped. This was built for Kotlin. It runs on top of Java annotation processing, and it allowed us to generate Java or Kotlin code. And this is important because we're all writing Kotlin, and having to write Java, having APIs that don't really work for us is not great. So Capt was kind of it was a way for us to run the old APs on Kotlin code and also allow us to write new Capts that were able to generate Kotlin code. And it was, yes, AP compatible. So now go all the way to September of 2020. First version of KSP was released by Google. And this is Kotlin first code generation. This is what we really like. Not everyone likes KSP. If you were here at some of the earlier talks, some people said nobody wants to learn KSP. I somewhat agree. It's a little complicated. So this is incompatible with annotation processing and Kotlin annotation processing. And that's because both of those things were tied to Java. We don't want to be tied to Java. That's bad. We want to be just writing Kotlin. We don't care about Java anymore. Now that we've gone through that history, we're going to get into a scenario and talk about actually what the point of this talk is. We're going to start with just these two lines of code, a log tag. And the tag has a value of droidcon, and you have a log that says log, and you provide a tag that says hello droidcon. And so the idea is that we want to provide context to this logger. And most people are going to be using a logger that automatically derives this context from wherever the code's executed. And that's great. We have three solutions that we can use to write this code. First is hard coding, the second is using reflection, and then the third is using code generation. And again, reflection and code generation are both forms of metaprogramming. First is hard coding. That's just you writing it or an LLM writing it for you. And you have a tag everywhere. Downsides of this are that if you refactor your code, you change your class name, it's no longer called droidcon, it's now called fluttercon, then it's still passing you the droidcon value and it's all wrong. But it works well. So reflection is where you're accessing the state of the class. And so the simple name getter on the class is technically a reflective API, and that's technically related to metaprogramming. And this is much better because then if you rename the droidcon class, it's gonna work. It's gonna update. And this is generally how like logging frameworks are going to derive the context to pass that context value to your logger. But we're gonna pretend that that's bad. And I mean, I guess if you do minify your code and your context, your class names change, or they got all changed down to like A and B and stuff, then that wouldn't work. But we're going to use code generation, and we're going to we're going to generate this code using KSP. And then we're going to basically do a 3-step process. We're going to find the classes that we want to generate. We're going to generate the code, and then we're going to use the generated code. So here's our goal. That shouldn't say object, but that's fine. We have a class called droidcon, and we're going to apply a tag annotation to it. And we want to be able to automatically generate a tag property for this class so that when I call log.d and pass tag, it automatically passes me the value droidcon. This is really what the code that we're trying to generate looks like. It's 2 lines of code. It's very simple. It's an extension property on the droidcon object. And it just returns the value droidcon as a string. So to set up a KSP, we have to set up 2 modules. We're going to have an annotation module that is our runtime module. Really, it's included in our code. It's included in our code. That's that tag that we had attached to our class. And we're going to have a Kotlin Symbol Processing module, which is going to be doing all the code generating. It's going to be hooked into the compilation process, and it's going to be operating on our code and looking over it. And lastly, we have an app module. And the app module is just going to include both of our dependencies. We're going to have a tagger project, which is going to contain our annotations. And then we have our KSP, which is called tagger compiler, and it's going to contain our processor. So here's our annotation. If you've never defined an annotation, there's a modifier in the class keyword. We're going to create a tag. We're going to annotate it with the target annotation. with the value class. And so that is going to tell the compiler that we want this only applicable to classes. And because we're providing context when you're calling a log from a class, we don't want it to be attached to functions. We don't want it to be attached to properties or anything else. It's just going to be attached to classes. And then we're going to set the retention on the tag. This is technically not necessary, but this explicitly tells the Kotlin compiler to throw away the tag annotation after compilation finishes, because we don't actually need it. And so this is just kind of like a clean way of saying, hey, Kotlin compiler, we only need this during compilation. Throw it away. It doesn't need to be included in the binary. So here's our tag annotation. And then this is the hard part. This is in the compiler module. First, we have to create a class that implements the symbol processor provider interface. And we're going to call that tagger symbol processor provider, which is a real word salad. This has a single function that we're going to implement, and it's a create function, and it takes an environment as a parameter, and then it returns that symbol processor. And so this is basically just a DI container. It's allowing us to do DI on our symbol processor, and it allows us to configure it, and it just gives us an extra step that is going to allow us some flexibility. But for this example, it really is just unnecessary because we're generating a very simple KSP. What we're going to do is we're going to create a tagger symbol processor, and we're going to pass the code generator that we derive from the environment. And this is going to allow us to generate the code. So before we move on, we have to pass this. Well, I'm missing a little piece here, but we have to set this value in some resource file somewhere. It's in resources, and it's some long path related to KSP. It's in the documentation, but we have to actually create this resource file so that KSP knows to load our processor provider. So now let's actually create the tagger symbol processor. It starts off similar to the provider. We're just going to have this single parameter. It's going to be code generator. That's how we're going to generate our code. And then again, it only has one function, but this one's called process. It takes a resolver as a parameter, and it returns a list of KS annotated. You can just ignore the return type for now. It's not really important. But the resolver is what allows us access to all the code that we're going to be operating on. It can find any code in the code base. It's very powerful, and it has access to everything. So let's implement this function. And we're going to try to fit it all on the screen. First, we're going to call resolver get symbols with annotation, and we're going to pass our tag annotation, the qualified name of the tag annotation. And what this is going to do is this is going to look through the entire code base. It's going to find all of the classes that we have annotated with that tag annotation, and it's going to return us the metaprogramming representation of that code. And we're going to have to do something with it. And what we have to do with it? Well, we have to get some information out of it, and then we have to generate the code. But first, what it returns us is just a KS declaration. And a KS declaration is Kotlin's way of, or really KSP's way of declaring what a class is, or what a function is, or what a property is. So almost anything can be a declaration. We have to filter and make sure that only the classes, we're only getting the classes. If you remember, there's a little detail when we're defining the tag that we said that we wanted it only to be applicable to classes. So really, we could just forcibly cast all of these to a KS class declaration and it would work, but we're just going to filter them just because it's annoying to like catch errors. And if we started catching errors and logging errors, everything wouldn't fit on the slide. So now we have a sequence of these KS class declarations, and we got to do something with them. First, what we're going to do is we're going to define a function for the getter for the code. And what you could do is you could just create a big string with all of your code. You can, use the multi-line string with a trim indent, and you could put all your code in there. But that's not a great way to do it, and it's not very ergonomic because you're going to have to add all the imports. You're going to have to format your code yourself. You're going to have to make sure that all the keywords are added, and it just gets it gets very verbose and it's just too hard to do. So thankfully, there's a great little library called Kotlin Poet that allows us to declaratively build Kotlin code. So funspec, as you might guess, is what we can use to create functions. And since we're creating an extension property with a single getter function, we're going to use the getter builder, and we're going to make it return a single statement, return $S. And we're going to pass the parameter to the $S as droidcon. We're going to build it. But that function is just ethereal. It's not attached to anything. Oh, but before we do that, we don't actually want to hard code the droidcon string. We want to actually derive the value of the class from the declaration that we're processing. So that way, this can be flexible and applied to any class. But now we have to attach the function to a property, and that requires us to create a property. So there's a builder for property specification. We name it tag. We set the type to class, and then we have to add a receiver because it's an extension property. And so we create a class name with the package name com.droidcon.droidcon, and that's a class name. We set it to immutable because it's a property. It's just always going to return something. It's no way to change it. And we attach the getter to that. And then there's this little extension function called addOriginatingKS file. And we pass the containing file of the declaration. So that means that for that droidcon class, it's going to pass droidcon.kt as the file. And this is important. It's a little complicated, but it's important because when a KSP runs, Kotlin has to know how the code got generated. Did it just come out of thin air? Was it attached to a class? And so when it's attached to a class, KSP can selectively choose to recompile and regenerate certain parts of the code. And this just tells KSP that, hey, if this class changes, we need to recompile this. So now we have a property with a function. And before we move on, again, we don't want to hard code the class name. We want to derive it from the declaration so that we can apply this to any class across our code base. Finally, again, we are working on a sequence, so we want to change this to a list because we eventually have to process it. And next, we have to check if this list isn't empty. And that's because KSP actually allows you to do things in multiple rounds. So that goes back to the return type of the list KS annotated. And you can actually tell KSP that, hey, I wasn't able to finish everything. I need to do some more work. And so KSP will actually run again. And the second time it runs, if you don't return anything, it'll just give you empty results. And if you have empty results, you don't want to overwrite the code you just wrote. So we're just going to basically return early if it is empty. But we now have to attach this function or this property that has a getter function to a file. And we're just going to naively throw all of these generated properties into one file. There's better ways to do this, but for the purposes of fitting all this on the slide, we're just going to create a single tags file, and we're going to add all the properties. So there's going to be, imagine a big KT file, and there's just dozens or hundreds or however many properties however many classes you annotated, there's going to be a property for those. And finally, we're going to skip over all of the hard stuff about how to use the code generator, and we're just going to call this extension function write to code generator. And all those extension functions that I keep mentioning, those are provided by the Kotlin Poet KSP library, and they wrap the complexity of KSP to allow us to write this a lot simpler. And this just writes that file directly to the disk, and then the true parameter just tells Kotlin that this has a lot of different pieces in it, and we may need to recompile it all the way if any one of them changes. And finally, we're going to return an empty list because that means we don't have anything left to do. So this is all of the code required to generate all of the tags and put them all in a file that we need. here's the generated code that we just generated. So there's the package name, which was automatically created for us. The imports were automatically added for us. And then we have our extension property just like we expected to exist. And it returns always going to return droidcon. And when that class changes, it will recompile and it will have its new value. And here we are. Here's how we can use it. We're just going to import this tag. It's going to be accessible to us because only if we're in the droidcon class, and we're going to be able to log it right there. So that's how to do KSP, and that's how to metaprogram with KSP. But now we got to bring it all the way back to the beginning where we're talking about Lisp and AI and metaprogramming. And that is the idea that AI is metaprogramming, and that when you are writing code with AI, you are doing metaprogramming. And that's important because what I just showed you up here with KSP is very technical and very deterministic, but it's very different from talking to an LLM and asking, hey, can you write a composable for me? And so I just want to just go over the differences and then try to pitch to you to maybe write a KSP, or at least just understand, hopefully understand a little bit of how they work. So I'm going to call them traditional metaprogramming tools: KSP, capped, annotation processors. I didn't even mention Gradle plugins, but Gradle plugins are also forms of metaprogramming. What they're good at is correctness. This code will run, you can run it 1,000 times, it will always give you the same result. That's valuable. Determinism, you know exactly what you're going to get out from it. You can write a unit test that you can actually write a unit test on your KSP that you can provide a specific amount of code and it will give you the exact code. And that allows us to be very confident in how these things work. That said, I'm sure you've all run into very annoying issues with things like Dagger, where you have some sort of incremental compilation error and you have no idea why it works. Sometimes that happens, and sometimes that's the metaprogramming tool's fault. Sometimes that's the Gradle cache's fault. And precision. We are handwriting this. An LLM sometimes is not going to be as precise as we want it to be, and we're going to have to modify it afterwards. But this, we can write exactly the exact code that we want all the time. On the other hand, AI is much more accessible. It's quite hard to write a KSP and trying to model the problem and think about how to solve the problem requires you to step back and think about a problem kind of the way you've never thought about a problem before, because you aren't thinking directly about how to solve the problem. You're thinking about how to stop yourself from solving the problem the way you normally would and solving it in a different way. And so AI is much more accessible. It's so simple. You can just ask it to do anything and it will do it. And it's also more creative, because where we have determinism in traditional metaprogramming, that limits the creativity of those tools. They really just generate, they're tools that are really, they're like Dagger. It's a sharp knife. It does a very specific thing. LLMs, they have a wide range of uses, and they each have their own value. That said, when we're using AI, it's very easy for us to start generating code and say, hey, wow, this saved me a lot of time. And so you get into these patterns where you're generating a lot of code. Say you're generating some test code, which I find it really good at doing, and I use that in my own work. Eventually you get into a habit where you're working with the LLM and you're saying, hey, can you generate me this code? And it will do it, no questions asked, but it will never question you as to whether you should have asked it to write that code in the first place. And if you end up writing a lot of repetitive code, maybe you need to think about abstracting that repetitive code. And that's not to say that you should go write a KSP, but the first thing you need to do is evaluate, do you have enough repetitive code that you're generating with an LLM that you can create a simple abstraction? Hopefully don't introduce tech debt, but create a simple abstraction so that you can stop putting up 1,000-line PRs every day with the same code over and over and over. So first, you got to deduplicate that way, and you have to identify the patterns. What you'll end up seeing with metaprogramming, if you ever try to want to get into writing a metaprogramming tool, is you'll see patterns that look similar. They have similar shapes, the code has similar structure, but it's different, and there's no way, you can't think of a way to abstract that. When you see those sort of patterns in the code and you're like, that looks really similar, but I have no idea how to make a function that can generate that code, that's where metaprogramming comes in. You can look at that and you can actually, in most cases, write a tool that can generate the code for you in an abstract way that will allow you to not write that code anymore. However, caveat, you have to evaluate the risks, because it's hard to write these tools. It's hard to maintain them. I don't have any contributions to Dagger. I don't have any contributions to Anvil. And those are tools that I understand and that I use every day. There's a high barrier to contributing to these sorts of projects, and it's important to know what you're getting into if you embark on developing one. But know that when you do develop a good one, it can save you a lot of time. It can save you a lot of review. It can reduce the amount of code that you're writing, and it can make your code a little more deterministic, which I think is important in this AI age where code is cheap and the code is also non-deterministic. So that's all I have. Here's some resources. I have a sample project that has this tags processor. It's very simple. The Google KSP project also has some examples, which I think are really good. Surprisingly, and I say surprisingly because documentation is usually not very good, I think the KSP documentation is really good. Shout out to Kotlin Poet. That is a great project, and you should never ever write all of your code in a text file by yourself. Always use something declarative like Kotlin Poet. If you have to complain about this talk, you can contact me, and that's it. Thank you.